Glad to be here. So my name is Nikhil. I'll be talking about event-driven microservices. I suppose there's a lot of talks on microservices in this conference. So basically the way I've structured this talk is I'm going to keep the first 2 points a little brief because I don't want to repeat. Everybody knows what microservices is. So briefly cover why you want to move to monolithic to microservices. But essentially where I want to get down is what are the challenges that you face in implementing microservices and how to get over them. In particular, I want to talk about the distributed data. I want to talk about how would you architect your services based on principles from domain-driven design, problems that you have associated with distributed data. What exactly do event-driven microservices, really bring to the table? A lot of people, they kind of interchange microservices and event-driven microservices. It's really not the same. There's actually very peculiar stuff that differentiates event-driven microservices from microservices, and they solve a particular kind of problem. So I'm going to talk about that. Moving on, I'll talk about some communication patterns, how microservices communicate with each other. Event sourcing is another hot topic. A lot of these things, really speaking, you hear all these fancy big terms, but they're actually reincarnation of old ideas that we know for decades, actually. So I'm going to talk about command query responsibility segregation, and towards the end, I'll talk about sagas, which is actually a distributed transaction mechanism to keep data in consistency. And I mean, because I'm kind of covering a lot of topics here, I'm going a little bit on the surface. I want to end with some resources. So if you want to dig more into the particular topic, I can give you some pointers on where to dig. So anyway, so let's get started, right? We have the old school approach, monolithic services, single service, single database, multiple clients, easy to test deploy. Everybody knows about them, and they don't scale, right? Large code base means your developer has more time to ramp up the code. One part of the code you change will break several parts. Essentially, the problem with monolithic services is there's no modularization. And when you don't have any modularization, you change one part, it's going to break a lot of other parts, right? There's too much of interdependency. This is a good pattern for simple applications, and this is a good point to start. And most of the startups generally would start with a monolithic, but it's a bad place to be in over the long run. So you want to have a transition at some point of time. So the brave new world is microservices, right? Essentially what you have done is you have decomposed your bigger monolithic into smaller microservices. And you can have heterogeneity in the sense you could have choice of languages, tools, technologies, stack frameworks that all come with microservices. The code is small, so it's easy to change and test and deploy. And you have these interfaces from where you can communicate. Truth be told, microservices is not a new idea. In fact, microservices is nothing but an application of object-oriented design principles applied to web service. How? When you think about how the evolution happened from imperative programming to object-oriented programming, right? The idea was that you have your software and you decompose it into these objects. And these objects have a state, a private state, your Java private methods, C++ private methods, right? And then they have the public methods or the interface. So whatever happens inside the object is known only to the object, and you basically communicate to the object from this outside interface. That's what object-oriented programming is all about. Microservices is nothing but taking the same principle and applying it to web service. So we are saying that instead of having one service, right, we have cluster of these services, and each one of these services have their own database, right? And you don't have access to that database. So this is the state. You don't have access to this state directly. What you have is you have this interface or the contract between microservice from where you can manipulate or do whatever you want to this service, and that would in turn change the state. So that's what microservice is all about. It's about loose services, and what it does is, like in object-oriented programming, you could have basically these different teams, right? You have modelization now, and you have well-defined interfaces. So you have these different teams that work on these set of classes, and as long as the interface stays the same, right, they can independently evolve. Microservices would bring the same kind of innovation into web service in the sense that you have these independent teams, As long as the contract between the service or the interface stays the same, the teams can evolve on their own. Of course, there are times when you need to change the contract. Typically, you would have it backward compatible, but there are times when you want to break. So it reduces the team interdependencies. It does not eliminate. In fact, really, I mean, I'm going to make a little bit of a bizarre statement, but microservices is basically an application of molecular biology to computer science. Why? Because that's what object-oriented programming was. Historically, one of the pioneers of object-oriented programming, right, he was a molecular biologist, Alan Kay. And in 1966, he was assigned to work on a software for US Department of Defense. I think it was Air Force or whatever. I don't remember too much of details. But so when he looked at the software, what he saw was he thought of software as a living organism, right? And he sort of wanted to model it based on how our living human body works. And how does our body works? Well, our body is composed of cells, right? And cells have cell membranes, which is the interface. And whatever happens inside the cell is private to the cell, and the system interacts through the membrane. So he brought this idea into computer science and created what was called as object-oriented programming. And what was those cells in biology became those objects in computer science. And what became the cell membrane in biology became what is called as public interface. So that's how object-oriented programming was born. Basically, molecular biology put in software. And since microservices is object-oriented programming put in web services, essentially by extension, it's microbiology put in web services. Anyway, the ultimate goal of all of this is faster innovation, right? Teams can evolve, they can innovate faster, they don't have interdependencies. All that good stuff being done, right? We have talked about the theoretical stuff. The question is, how do we actually design the system, right? We need some strategy. So I'm going to digress a little bit from microservice and introduce domain-driven design. And then I'm going to come back and show how domain-driven design actually would help you architect the system. Domain-driven design itself is a very big topic, and I'm only going to give a 1-minute kind of introduction to domain-driven design. I do have some resources at the end, right? So what domain-driven design is basically, it's an approach where your implementation is connected to a model of the system, right? So let's say you're implementing some banking system, you have some objects there, like bank account, savings account, whatever. You model them. If you want to do a object-oriented programming, you would model them as classes. If you want to do a functional programming, you would model them as your algebraic data types. But your physical model, right, is mapped into a software model. And then as you develop the system, you kind of evolve. As the model evolves, your system evolves. There are these building blocks of DDD. These are 4 main ones, but this is no means an exhaustive one. Like I said, DDD itself is a very big topic, right? Entities, value objects, and then you have these bounded context, which is like mini maps or mini models inside main maps, and aggregates. We're going to touch a little bit on aggregates because this is the stuff that is actually important from a microservice point of view. And when you look at a software consists of layers, right? Again, this is a simplified picture. If you go to the literature, you would have what is called as an hexagonal model. You have an onion architecture. There are variants of this model, but I'm really putting a very simple picture of you have a user interface, typically runs on your client, right? You have the application layer. So these are the services. And then you have the domain layer where all of these value objects remain, right? Your physical entities. Most of the time, they are immutable. And then you have the persistence layer. And typically, domain layer can access the infrastructure layer, but not the application layer. So you have a layered approach to software development. So let's expand on aggregates, because this is the stuff that actually is important and helps us design, architect microservices system. Aggregate is a collection of objects that you can treat as a single unit. For example, if you're designing an e-commerce application, your order is an aggregate. So order would have an order ID, and order has components. So an order would consist of payment information, shipping information. It would have a list of products, product items. It will have quantities and so on. You could treat this whole thing as one particular object referenced by one root, which is your order, right? And it has a strong compositional relationship in the sense that if you destroy the order, everything in it gets destroyed. So it's not it's not a reference. It's actually by itself an object. And when you look at it, a domain model is essentially a collection of aggregates. Now, there are different ways on how you combine aggregates, right? So because let's say your domain model consists of 50 objects, you can have like, okay, I'm going to put an aggregate across these 10, and then you have another aggregate. So there are multiple ways of how you can build the aggregates and sum it up in domain model. So there's no unique relationship, but essentially whatever combination you took, domain model is nothing but a collection of aggregates. Coming back to the microservice world, what aggregates give you is the boundaries for partition. So we talked about the fact that if we want to decompose our monolith, or we want to have our functionality divided into services. The question is how. DDD provides you that answer. So DDD says, well, you could have an order service. This is your aggregate, and you can have one or more aggregate within one service, right? And these aggregates are referencing the customer, the product. By no means this is the only combination, right? I can have an order service and customer service combined into one and product service combined into two. So there are multiple ways of combining, but essentially what DDD gives you are boundaries or the seams from which you can actually cut out the functionality and put them in a service, whichever way you want to do it. Okay, so everything good. I mean, we have data distributed, but obviously we have problems with distributed data, right? Microservices have their own advantages. Microservices do have their own disadvantage. You have different data sources. How do you keep them consistent, right? I ordered something. I want to tell the customer service so customer history gets updated that I have ordered something. Obviously, the customer service is a separate service having a separate database, so somebody has to tell that. So you have an issue of consistency. Related to that, how do I query the data? Because earlier in the monolithic world, all my data is in one database, right? Now it's scattered all around. I don't have access to these individual databases. I do have access to the services that can access, but I don't have direct access. So I want to build a query. I want to build a query that has show me all the products that show all the customers have ordered. The problem is the information about customers is in one service and information about product is in another service. How do I query across the two services? I can't use ACID transactions because I don't really have atomicity, right? So here's a simple SQL query. I want to select some addresses and I want to select some price. I'm building some query. But as I said, this is private to customer service. This is private to the product service. I can't run this query in one service. One would argue that you could potentially use two-phase commits. And probably you're right. But there are problems with two-phase commits. And this is actually a very big problem, distributed data in microservices, right? Whole lot of reasons why two-phase commits is a problem. The coordinator becomes a single point of failure. It's very chatty. When we talk about these services, we want to talk about high throughputs. This decreases the throughputs. And of course, availability is very important for us. The reason is every minute that our service is down is every minute we are losing revenue. I mean, think of it. If Amazon goes down for 5 seconds, how many millions of dollars do you think Amazon would lose for those 5 seconds, right? So availability is something that we cannot afford to essentially sacrifice. We really can't solve the problem. We can't have everything, right? CAP theorem says that you can't have consistency, availability, and partition. Like I said, availability, we can't touch. Partition, really we can't, because we have these services running in different data centers across the globe. We have customers in, let's say, UK, customers in America. We can't really, the network partition goes down, it's going to be a very big problem. But we could sacrifice on is consistency and move to what is an eventual consistency. So what eventual consistency would do is I would design my system in such a way that given a period of time, my data would be synced. So it's not going to be available immediately, but it's going to be available given an amount of time. And usually that time is often a short period of time, right? Few seconds, few minutes. So it's usually not a big problem in the sense that let's imagine that you are living in UK and I go to Amazon or Jet, I order something, right? The database is updated in UK, but it's not updated in US. It would take about 1 minute. What's the chance of me going to America within 1 minute and logging in and not seeing the data? I mean, if somebody has logged in within 1 minute of me being UK, I probably would think my account is hacked. I'll have bigger things to worry about, honestly, than data consistency at that point. So in most cases, consistency can be replaced by eventual consistency, provided that eventual part usually stays within a threshold. And this is what event-driven microservice architecture brings to the table. So event-driven microservice architecture is a subset of microservice architecture that would let you design system in such a way that it will be highly available, it would be partition tolerant, and eventually consistent. A lot of people, they kind of confuse between microservice architecture and event-driven microservice. They kind of interchange. They're not really exactly the same. Event-driven microservice solves a particular problem. There are other ways to solve that problem. It's not the only way. There are other software architecture patterns that you use, but this is the most common one, because usually this is the one that would let you have near 100% availability, which is very critical for most of the businesses. So what is event-driven architecture, right? Again, a fancy term, but event-driven architecture is something that generally we kind of use it on an everyday basis. So definition-wise, you have an event, something happens in your system, some way it is broadcasted. There are people who listen, and listeners get notified, they may take an action. It's really a highly distributed, loosely coupled architecture. What do I mean by that? I mean by that the person who sends a request would generally be not aware of the person who receives it, right? And very critical, it's often used for asynchronous flows of information. A very common and a very layman and probably a silly example of event-driven architecture is what you had today morning, the fire alarm. Somebody notifies you of an event. There's a fire alarm, right? As a listener, you act on it, or you chose to stay in the building for whatever reason. The sender does not know who the listener you guys are, right? Sender just broadcasts an event. The medium of transport is air, and the listener receives it, right? And everybody is kind of independent of each other, and it's an asynchronous flow of information. The person who made that announcement was not aware of the fact that whether you actually heard it or whether you actually took any action, right? He just made an announcement and that's it. He has no visibility into what really happened. And this is also one of the downsides of event-driven architecture, is because of that asynchronous flow of information, you actually have a loss of visibility. But it's still an advantage because it gives you high throughput, right? I just send a message. I don't have to worry about getting a response, waiting for a response, being busy until the response happens. And most important, I send a message, even if that component is not available, it's still fine. It'll just get queued, and whenever the component backs up, right, the person would hear that message and act on it if he has to. For example, I made a message, somebody was in the bathroom, probably didn't heard. When he or she came out, right, the message was still being resonated. We don't have a queue, really speaking, but let's say they made multiple messages. As soon as the person heard the message, they hopefully took an action, right? So in a way, that component was down for a short while, but it was not a problem. Okay, so we talked about communication. How do we communicate? Well, you have a direct messaging, right? So let's say somebody places an order, it goes to a customer service, goes to a product service. The order has an ID, so you can track. The customer service would look at the payment information for the customer. The product service will just check and send it to fulfillment service. Fulfillment service waits for the payment service to get the message. All of these calls are non-blocking, right? And when it receives the confirmation for payment, it sends to shipping information, and shipping information delivered. In my example, how I correlate is, this is like if all of us have to talk to each other, we just talk to each other directly, right? Not through an announcement or a loudspeaker. So that's like a direct message. It's easy to implement. In the service world, it's very easy because you can have all of these serverless and have all of these microservices implemented as serverless functions. So it works very well from that point of view. But the problem is it increases the coupling, because if the order service wants to talk, it has to know whom to talk. For example, if I want to talk to you, I need to talk to you, I need to know. Whereas when a person who made that call that there is a fire alarm, he doesn't really have to know who the people are. He just makes, and that's it, done. So that's the reason why this is an approach which is often not used, is that it has a lot of coupling. The components actually have to know about each other. And when you increase the coupling, what you have really done is you have increased the dependency among the teams who own that service. And the moment you do that, you've actually slowed down the innovation. So you basically have defeated the purpose of why you actually moved to microservices in the first place. Another problem is it's difficult to scale. For example, I want to create a new scenario, right? I also want something like a fraud service, for example, to be there and checks for every order. And if it's a fraud for some reason, it thinks it's a fraud, issues me an alert. When I do that, I create that new service, but now I have to change the order service, right, to incorporate the logic that not only do you have to talk to product and customer, you also have to talk to fraud service. I can't just plug in a new scenario. Just the fact that I have to plug in a service, I would have to change a lot of other components. And it gets very difficult. I mean, this is a very simple example, but when you have 1,000 services talking to each other, right, it's not that easy to comprehend. So the more common approach that we have is a message broker, right? Kafka is one very well-known message broker. I think in the Java world, I'm not too familiar, but there's a RabbitMQ. Different vendors also provide you with. Microsoft Azure has Service Bus. I think there is something similar with AWS also. And what it is that you have this message broker that is central. So you can just send a message there, and anybody who's interested in listening can just subscribe to that, right? So if I use Kafka as an example, right, let's say this message broker is Kafka, you would have various topics, right? So I would have like, okay, product service, product information, service information topic, and anybody who's interested can just listen to that. The product service does not have to know or worry about who are the people listening. That's the job of the broker. And if the component is down, the broker is actually queuing up. In this scenario, let's say I want to introduce a new scenario of fraud service. I can have that fraud service spin up and come down and just start hooked up to the message broker and starts listening. So here, I don't have to change the product service or anything else. The service just comes up. And if that service just goes down, it does not affect. So this is the reason why this pattern is actually more popular. It has several benefits, right? It is more scalable. I can support more scenarios. It has increased decoupling. The components are independent of each other. A better error control in the sense I have more visibility. Message broker, I can keep a lot of logs and traces on message broker, but you want to ensure that broker is highly available. So that's a drawback for this, because if the broker goes down, good luck with that. Okay, so let's talk about real world scenarios. And one of the things that you always find is that we study a lot of these different software patterns, right? But in a real application, there is usually not one or two, but there are several technologies that would work together, right? So let's take a simple example of something like jet.com or amazon.com, right? You have a customer-facing website, so I place an order, right? And then you have the websites that work on the back, the fulfillment, and then you have these other websites. So I'm going to call tier 1 services, the ones that customer actually interacts with. The tier 2 service, ones that kind of impacts customer indirectly, and tier 3 that has no impact for customer. A good example of tier 1 is basically order service. You place that order. If that service goes down, you can't place an order, finish. The second tier 2 is like fulfillment service. If that service goes down, your order would be delayed for some time until the server comes back. Usually if it comes back within 10 minutes, you won't even notice. So there is an impact, but it's not a direct impact. And then there's tier 3, let's say monitoring service, right? To you as a customer, if Amazon or Jet is internally monitoring their service, you don't really care. If that service goes down to a customer, you have absolutely no impact. God forbids if there is an exception or a bug or something like that, that would be their headache, so it will be a problem for them. But as far as customer is concerned, you have no impact. Typically, how you would do it is, you would put your tier 1 services not in event-driven, but more in request-response form, which is more of a synchronous. Why? Because you have a lot better error control here. Let's say the order service goes down, or order service calls another service, and that service is not done. You want to notify the customer, right? One of the problems with asynchronous information flow is the information goes, and you don't know what happened after that. Did the person get that message? Did he act on it? So for direct customer-facing service, you generally would not use an event-driven approach. You want something synchronous. Something happens, the customer order service can immediately notify, hey, I'm down, something went wrong, sorry, try back again 5 minutes. The tier 2 or tier 3 service is more of an event-driven, right? Going back to my earlier example of the fire alarm, if I was the person making an alarm, tier 1 would be me coming and talking to you, please leave this place, right? I have a direct control, I can see you left it. And if not, I can harass you or whatever, threaten you. Tier 2, tier 3 would be me making an announcement and hoping you just acted on it. Anyway, so let's introduce event sourcing. It's one of the very popular, okay, I messed up slides a little bit. Okay, let's start here. So it's actually one of the very popular paradigm or software architecture pattern that you are all the time, but truth be told, this is something that we have been using for decades. Actually, event sourcing was invented much before computers. What event sourcing says is that if you look at the state of the system, right, and a change, what you do is you model that change as an event. So your state is nothing but a collection of that events put together, right? You store that event, you don't really store that state, and you just store that event, and you can build up your state by collecting all these events. And what it does is enables you to roll back in a particular time. So you have the whole history in saying, what was my state of the system 2 days from now? Very common examples of event sourcing, something that we all use, are things like banks and version control. Banks, right? How's bank an event sourcing system? You open an account, your state of the system is the money in your account. You open up with an initial state 0. Every transaction that you do, you put money, let's say I put $10 plus 10. If I withdraw, it's minus something, right? So if I store every transaction as a positive or a negative integer, I can reconstruct how much money I have in my account by just summing it up. So rather than storing the account history in terms of how much money I have at a particular time, I just store the transactions, and I can build up my state anytime. Event sourcing has a huge advantage, which is the reason why something like banks would use it, is you can combine and recombine these events in any way you want. For example, let's say that I've stored all the events, right? I've stored all the transactions, and I'm using credit card, and you come to the bank and you say 3 days ago there was a transaction which was a fraud transaction, so I want it to be removed. If the bank does not have information of all of these transactions stored individually, there is no way it can do that. But let's say it has stored every transaction. What it can do is, okay, fine, let's do this. Let's build up the state. Let's just recombine all the events, except that event that you're claiming is a fraud. So it can still build up all these events from scratch. Just one event that you claimed was fraud, it removes it and builds up the state. That's event sourcing. Another common example of event sourcing is version control system, right? Your state of the system is your software. And every time you commit, you're basically committing a delta. And I don't know internally how Git works, but I would think that it would have some kind of data structure that would aggregate, all of these deltas and builds up, this is the state of your source code. And you can go back and forth in time. So you can just look at a Git log and you can say, well, I want to go back to my state of the system 1 day ago, or git hash commit ID, and it can just, git change or whatever. I think it's the git checkout commit ID, and it'll go back in time. So event sourcing would allow you to do that, but it has one drawback. Every time you need to know the state of the system, you actually have to build it, right? That's not practical in a lot of cases. I mean, if I want to know my account history, are you telling me that each time I want to know that you're going to add up all the transactions I did since last 10 years and tell me what my state is? So in order to mitigate that problem, there's a common pattern in event sourcing, which is snapshots. So what you would do is you would take like a regular snapshot. Let's say I'm taking a snapshot every 24 hours. At 2 o'clock in the night, my system would basically aggregate all the events and store a snapshot of the state. So if you want to know what was my state of the system at 6 o'clock in the morning, I don't really have to roll back on the last 10 years. I just have to roll back 6 hours because my last snapshot was at midnight. So what the snapshot mechanism does, it mitigates this drawback of event sourcing that you don't really have to combine all the events from scratch to build up your state. You do have to combine a little bit, but not all of it. Of course, snapshot adds its own complexity. So what are the benefits? Okay. So you have 100% accurate audit learning. You can go in time, applications can process. I'll expand on this a little bit. Applications can process the same events, but create a different view. You obviously have some drawbacks. You're talking about events being sent, states being built. There's no strict consistency, right? It's an event-driven system. It adds complexity, and you have longer boot times. But like I said, snapshots can help you. I'll expand on this point. Think of it as a Facebook, right? In your Facebook profile, you have an event. You take a photograph, you put a post, everything. That's all an event. And you have all of these applications listening to that event, but you're trying to create a different view from it. For example, I have my timeline, I have my personal information session, and I have my photographs. If I post a photograph, it comes on my timeline receives it, posts it. My photograph application receives it, posts a photograph. My personal information session doesn't do anything, it just ignores it. Then I have a second event. Let's say I got married. Still comes on my timeline. The photo says, I don't care unless you put a picture of your marriage. And then my personal information section, which says from single, married, right? So what you have is the same event coming, different applications listening to that event, but creating a different view of that. This is actually particularly useful in one of the patterns called CQRS that I'm going to probably cover next. CQRS, or Command Query Responsibility Segregation. The name sounds a little scary, but it's dead simple. What it is it separates the read and write, right? And it's actually a must for event sourcing. And the reason why it's a must for event sourcing is because you don't have the ability to build a view directly because your data is scattered, right? In order for you to query, how would you query? So how it works is that you separate the read and write, right? Write would store the event, it will go to the database, and read service would actually read these events and create these different views. And you could have more than one, like I said, you can have more than one applications creating different views. So they create these views, and every time you want to query the system, you actually would query from read, which was going to be building up the state in the read service. The drawback here is, and I'm going to cover that in details later on, is that you have, every time you want to update a system, the write service has to write to DB and the read service has to read it, so there's a lag. But essentially with this pattern, you would be able to query your state of your system. So earlier I had shown one slide, right, where you want to run a SQL query, and one of the databases with the product and one of the customer, how do you deal with it? This is how you deal with it. You would have these read services that would build these models that you can query. And this is the reason why CQRS pattern is actually must if you're using event sourcing. Like everything, CQRS brings its own benefits and drawbacks. If you're using event sourcing, well, you don't have an option, sorry. It improves the separation of concern. You can have for a lot of applications, usually you will have a lot of reads and very little writes, right? So you can optimize for, I'm going to optimize for read. My writes could be basically blocking calls, but my reads could be non-blocking asynchronous. So that improves the scalability. You also have multiple scalable de-numerized view. In simple terms, this is the Facebook example that I gave, right? So you have these events coming and different services, timelines, photographs, personal information. They are building these different views from the same set of events. Drawbacks, you have increased complexity. is potential code duplication and replication lag, right? There's no strict content consistency, which is a problem in general with event-driven microservices. Sagas. So sagas is a mechanism that you actually use to keep the data consistent. Sagas is actually originally based on a 1987 paper. These guys, at that time, I think Hector now is in Stanford. At that time, he was in Princeton. And it was basically for database, right? You wanna put queries on the database, and then you can't really hold the logs for long. So that was how they invented sagas, and it's now adapted for distributed systems. The original Saga, obviously, because you were talking about database running on one node, did not actually have to deal with issues of asynchronous and partial failure. The distributed Sagas mechanism that is now we use in microservice actually has to account. So what is a Saga? What Saga basically has is, rather than having a transaction as one distributed transaction across services, which you can't have, it's generally an anti-pattern, you actually distribute it across services. So you have transactions, right? And you have a rollback transaction. So if something fails, right, you can roll it back and revert it. Here's an example. So long-running science, you have a compensating action. So this is like, say, deposit check. I want to deposit the check, sender has enough money in his account, check credit service sends a withdrawal service, right? If the money is on hold, and let's say he did not had and it failed, it can go back. And let's say this was all fine, you go and deposit, There are interesting scenarios actually when you think about it. This is a very simple example, but let's say I transfer money to you. The money gets deducted from my account and everything's good. And as it was going to go into your account got canceled or closed. You closed your account. Where does the money go now? So you have to take into account a lot of these scenarios. And in a simple model, you have a compensating action that money would come back to my account. But what if I close my account also? So what happens to the money, right? Your account is not there, my account is not there. So it can lead to complicated scenarios. Another pattern that we are talking about is distributed Saga. So distributed Saga is basically one particular implementation of Saga. This actually was, I don't know if it's still being used, but this was originally developed at Twitter. So there's a talk by Katie McAfee about all of that. They talk about, you have a Saga execution coordinator, SEC, and distributed Saga. You can have parallel applications. So you can, let's say I want to put a vacation, I book a car, hotel, flight. These are all parallel. It's a directed acyclic graph of actions, and each one of them have compensating requests, right? So I can have a payment, and then I can end the Saga. If anything fails, I can go back. So let's say I booked my car, I booked my hotel, but the flight failed. So it reverses it and says, okay, let me go back and cancel. But because it's a directed acyclic graph, right, I can parallelize it, so it increases the throughput. And then you have the logs, the Saga logs where everything is being recorded, so you know what's happening. And requests have to be idempotent because it has to be must. Let's say because you have parallelization, you don't really have isolation. You can have same action repeated multiple times. You should be able to kind of abort. That's a property of request because, hey, it can fail. Compensating requests also have to be idempotent, commutative, because you don't really have any kind of order. And they cannot abort because if the transaction failed, I have to undo the transaction. I mean, imagine you trying to book a car and then I have to roll back and I say, well, I can't refund you the money, right? That's really kind of very awkward. Towards the end, I would just end with some of the resources. So Building Microservices, very famous book. Everybody probably knows about it, just talks about microservice. This, Eric Evans is known to be basically the pioneer in DDD. So this is a book that explains DDD. It's actually a big book, 500-page book. It's called the Blue Book in literature. If you don't want to read a 500-page book, there are other books like Implementing Domain-Driven Design by Vince Vogue, which basically is kind of a condensed version of this book. Chris Richardson, it's actually, I think it's right now in preview. It's going to come out in June. This is a very good book. I actually got an early release of this book. It talks a lot about all of the sagas, and there are different versions of saga, orchestration, choreography, and so on. Because of limitation of time, I could not go into too much of details. There are some excellent talks, how DDD is used to develop microservice architecture, microservice.io, excellent resources for saga patterns, the whole talk about how Twitter used distributed sagas, you have it here, and questions.